All right, let's try again. I recorded this and then somehow I clicked something and deleted it, or it became a very short file with nothing in it. So I was very angry. Now I'm trying to gather my composure and do it again. Okay, students, back to the drawing board. Take two. All right. We're moving on in chapter 10, right? Last thing we did was scattering parameters, right? Got some examples on scattering parameters, etc. Now we're doing microwave devices, right? So we're going to start off with right couplers and dividers. Okay, right. So first off, right, let's look at circulators. So again, read this section. Pretty straightforward. Stu does a nice job of describing this. So here's a circulator, right? How are we going to describe the performance of this thing? What does it do, right? So whatever I put in, ideally, right, whatever I put into port one is going to come out of port two, and nothing comes out of port three, right? Whatever comes into port two, all of that comes out by virtue of these arrows, comes out of port three, nothing comes out of port one, etc. Right? So we're going to describe this thing, this device, via the scattering matrix, right? So the scattering matrix for this device is as follows, right? 0, 1, 0, 0, 0, 1, 1, 0, 0. Ideally, right? The actual the scattering matrix for an actual device won't have these ideal numbers, but they'll be reasonably close to these values, right? Rather than 0, it'll be something small. Rather than 1, it'll be 0.9 something, right? So what kind of application might we have on a device of this nature, right? A circulator. Well, here's our transmitter, right? So the power comes out of the transmitter, uh, fed into fed into port one, so it's going to come out of port two, and we might attach an antenna to port two, and so there'll be a wave that radiates from the antenna. Perhaps there's a target out here, right? This might be a radar application, and so the incident wave reflects off of the target and comes back into the antenna, and then the return signal into the antenna is because of the circulator, right, is all fed into port three, where our receiver resides, right? So we're taking the we're taking the return from the target and processing it in the receiver to determine what Doppler effect, Doppler, and therefore range or whatever other parameter we're interested in, uh, etc. Okay, and also, right, the receiver is very sensitive, right, because it has to pick up very weak signals reflected from the target over typically large distances r. Okay, so we know from Friese transmission equation, the forward is r squared, goes like power goes like 1 over r squared. The back goes like 1 over r squared. So in the radar range equation, which we never developed, but I think Stu develops that in the chapter on antennas, you could read it there. So it goes like 1 over the r to the fourth. So that's a weak signal back from the target for large ranges. And so the signal fed into the receiver, right, from port two to port three is weak, right? So the receiver has to be very sensitive. And so because of its sensitivity, you don't want to be bombarding the receiver with power from the transmitter, right? So you don't want to overload the receiver from power from the transmitter. So you need to have port three and one isolated in the ideal case. Okay, so that's one application. All right. So, right, what about non-ideal? Right. Well, we're going to characterize the circulator in terms of its insertion loss, right, and its isolation, right. Remember how this goes, right? Insertion loss from to the subscript from to right to left from to. So it's minus 20 log magnitude of S21 from port 1 to port 2. From port 1 to port 2. We want that to be right we want that to be 1, right? And so log of 1 is 0. So we want the insertion loss to be 0 dB, which means that in the signal propagating from port 1 to port 2, there is no loss. The device itself doesn't absorb any of that energy, right? Well, that's unrealistic. So S21 uh, won't be the insertion loss won't be 0, but it'll be small, right? If this thing is well designed, and then right insertion loss from port 3 to port 1, right? We don't want anything out of port 3 that we put into port 1, and so ideally that'll be 0. Log of 0 is minus infinity times minus is plus, and so we want S21 to be we want an insertion loss of 0, and we want an isolation of infinity, right? So we want this port to be isolated, this port to be fully coupled. And then what else do we have? Well, we've got S11, right? And so that's just the reflection coefficient looking into this port, which is 1 plus the right? And so that's the reflection coefficient. And so we can characterize that as the VSWR on the feed line, right? It's a V max. This is a standing wave if there's something reflected. So it's the maximum voltage divided by the minimum voltage. And so, right, VSWR is a number between 1 and infinity. Here, the magnitude of gamma is 1. Here, the magnitude of gamma is 0. So nothing reflected at the port means the SWR on the feed line is 1. Good. Everything reflected at this port, the SWR on the feed line is infinity. Bad. Okay, so this is good on this side typically and bad on that side. So, right, Stu's got a little example in 1010. Look at that. And so, given the insertion loss, isolation, and the VSWR, find the scattering parameters, right? Well, if we know these numbers, we can simply back out scattering parameters. Then we can fill this up, right? We can fill this matrix up, and we'll have the actual scattering matrix rather than the ideal scattering matrix. Okay, so circulators, simple application, right? How it's characterized in the non-ideal case, we characterized it via the insertion loss, isolation, and VSWR, which gives us S21, S31, and S11 respectively. And then we get the other scattering parameters because of symmetry, right? Because of symmetry. All right, page 1. Right. Right, so let's look at, right, here's some 3-port dividers, right? Now let's back up and mention that over here, right, these scattering parameters, right, and the isolation, insertion loss, and VSWR also will be given on the device from the device specifics, right, as a function of frequency, right? So this thing operates over some range of frequencies, and these device parameters will, in general, vary as a function of frequency. So this device has limited bandwidth. So if you're trying to buy a circulator for X band, then right, you'd have to look at the device parameters as a function of frequency from over the range of frequencies from 8 to 12 gig. That's X band. Okay, right, might be a radar application. Okay, so here we go, right, with a 3-port divider. All right, this is a resistive power divider. Okay, so what's its intent? Well, as the name implies, it's supposed to divide the input power into equal output powers at ports 2 and 3. And then hopefully not much of the input power would be reflected, right? And so this shows, right, that this is the scattering matrix, right, for this particular microwave device, so this resistive power divider. So it's S11 is 0, right? We should be able to show that, and we will momentarily, meaning that none of the input wave is reflected at this port, right? So we know then, before we even do any analysis, is that the input impedance looking into port 1 here, right? This is port 1, this is port 2, this is port 3. Right? This is our reference port. None of that input power is reflected if S11 is 0. And then, right, 1/2 here, 1/2 here. And so, right, that gives you S. This is 2, 1, in, 1, out, 2. Right, so that's a half. S3, 1, in, 1, out, 3 is 1, or times a half is a half. So 0, a half, half. So half of it, the wave intensity here is a half, right? So the power is going to be proportional to the square of that, right? So it's going to be a fourth. Right? So we're going to see how all that works out in a minute. Okay, so let's try to get S11, right? So S11 should be Zn minus Z naught over Zn plus Z naught, right? Well, what's Zn? What impedance? And that's, right, S11 is calculated with V2 plus equal to 0 and V3 plus equal to 0. How do we get V2 plus and V3 plus to be 0? We terminate the T lines here in their characteristic impedance, Z naught, Z naught. Well, if we do that, right, since this line has a characteristic impedance Z naught, it's terminated in Z naught, a resistor of value Z naught, then the impedance right here is also Z naught. And the impedance right here is Z naught, right? So I've got Z naught here plus Z naught over 3. That's 4 Z naught over 3 between here and here looking that way. 4 Z naught over 3 between here and here looking that way. And so we've got 4 Z naught over 3 in parallel with 4 Z naught over 3, which is 4 Z naught over 6, right? Equal parallel impedances split in the equivalent is half of one of them. And then I add that to Z naught over 3. That should be my Zn. So, right, that's pointed out here. So Zn is essentially, we can argue and demonstrate here that Zn is Z naught. And so when I compute the reflection coefficient at this point, as expected, we get 0. So all that circuit theory right there and transmission line theory did indeed show us that the input impedance at this location was Z naught. Right. So now I want, right, I want I want to be able to derive S21 and S31, right? What's out of port 2 given what comes into port 1 and what comes out of port 3 given what comes into port 1. So how am I going to do that, right? It's going to be a voltage division thing, right? So, right, the transmission coefficient, right, is 1 plus the reflection coefficient, right? So T is 1 plus gamma. So if I take that reflection coefficient here, add it to 1, well, the reflection coefficient was 0, remember? So I add it to 1, I just get 1. So this is going to be 1, right? And then that voltage, if I want the percentage of that wave that ends up at this pair of terminals, right, I simply need to do a voltage division between the equivalent impedance here and this impedance. But it's the equivalent impedance here with these two ports terminated, right? Because when I'm computing S21, I've got to have all other input voltages, right? In, out, all other input voltages set to 0. So I do that by terminating these. Right? Maybe I'm beating a dead horse there, but that's important when you get ready to understand why you calculate these things the way you did. Okay, so the voltage division between here and here, right, is just as we discussed, it's 2Z naught over 3 divided by 2Z naught over 3 plus Z naught over 3, right? So the impedance right here at this pair is looking that way and parallel looking that way is 2Z naught over 3. So it's that one over this one plus that one. That gives you 2/3, right? But that 2/3 voltage wave has got to be divided again between what I see here and that, right? Voltage divided again because because of the input impedance at this location, right? Whatever is here is also out here, and I'm trying to get all the way to this port. So S21 is 2/3 times, right? Z naught over Z naught plus Z naught over 3. So that's a half. And so again, we get, uh, we've proven basically, going through the circuit analysis, prove that uh, that this indeed is the scattering matrix of that resistive power divider, right? So there's other power dividers, right? This is one manifestation of a power divider. If you look in the text, right, you've got the Wilkinson power divider and you've got the resistive power divider. He presents two different topologies to achieve a power division. Okay, let's look at that real quick. 10. Lost my place. Again, I'm having to do this twice. A little frustrating, but all part of a day, I guess. Right. So here's our resistive power divider. Right. Page 570. Here's the Wilkinson power divider. Right. What differences do you notice immediately? Well, this one's got resistances here, right? So those are going to absorb some power. So you're going to have some significant insertion loss here, right? Over here, the way it's done is these are characteristic impedances. They don't absorb power, right? What's the difference between a characteristic impedance and a regular impedance? Well, characteristic impedance is the voltage traveling wave divided by the current traveling wave. This impedance is a power loss type impedance. Similarly here. So you're propagating through, you're dividing by virtue of a power loss. Here you're dividing, at least to some degree, by a lossless device, right? Just the T line itself. Now there is this 2Z naught over here. So you're going to have some insertion loss, but it's not going to be as severe as it is with the resistive power divider. And so, as Stu points out, the Wilkinson divider has only a 3 dB insertion loss compared to the 6 dB for the resistive divider. Right? So that's an advantage. Okay, right. So power dividers. Right? What again? What might you do with these things? Well, here's one application. PN, right? Some PN. We're going to split that, and let's go into another device identical to it, and we're going to split that, and then we're going to go into another power divider and split it. Right, so we could continue this process, but let's just stop here. I think the intent is shown. These are antennas now, right? So essentially, power half this way, half that way, Pn over 2, Pn over 2, and then it splits again, Pn over 4, Pn over 4, Pn over 4, Pn over 4, and so, right, 1/4 of the power goes to each transmit antenna. Right, so we might also have, who knows, might also have some phase shifters in here. Phi1, Phi2, Phi3, Phi4. And so now we can adjust both the amplitude and phase of the signal fed into these antennas so we can steer the beam in space, etc. Right? So this is a simplification, but suffice it to say that would be one application of a power divider. Now, we haven't talked about phase shifters, but that's another microwave device that would need to be constructed and could be analyzed via the scattering matrix representation as well. Okay, so application. Let's throw that away. Okay, so resistive and Wilkinson, right? The resistive 6 dB insertion loss, Wilkinson power divider, only 3 dB. Okay, right. Moving on. Right. So now what are we doing? Couplers, right? This is the general generic picture for a coupler. Okay. Just generic representation. So here's the way we're thinking about this. Port 1 is the input port. Port 2, excuse me, is what we call the through port, right? So that's your through port, and then port 3 is the coupled port, right? So some of the input power is some specific amount of the input power is coupled to port 3, right? If I have a 10 dB coupler, then typically what that would mean is that the power fed into comes out of port 3, the amount of power that comes out of port 3 relative to the amount of power that was input to port 1 is 10 dB down, right? So it's a tenth. The signal strength here is a tenth of what it is at this point. It's a 10 dB coupler, right? And ideally, the rest of it, the through port would be 9/10 of that. And then the isolated port, ideally, none of the input power here would come out of the isolated port. So that's the ideal coupler. And so there's two ways of this generic representation for a coupler can be manifested in different ways in the circuitry. Right? We're going to talk about that. But you've got basically the symmetrical or 90-degree coupler, and its scattering matrix is represented this way. And then you have the anti-symmetric or the 180-degree coupler, and its scattering matrix is represented this way, right? The 90-degree coupler has J's in there, as you might expect, right? Because J is the square root of -1, which is the square root of 180 degrees, which is etc. Right. So J is a 90-degree phase shift. I mean, not go the other way. It didn't seem to make much sense when I tried to do it. So anti-symmetrical, right? So here you're going to have 180-degree phase shift, just minuses. So, right, how's this going to go, right? You're going to have the coupling coefficient, right? How are we going to characterize the coupler? And again, all of these are going to be a function of frequency. Don't forget that. So you've got the coupling coefficient, right? Output of port 3, input to port 1. Output of port 3, input of port 1. So it's the power out of port 3 divided by the power into port 1 minus 10 log of that. So that's your coupling coefficient. Right. So the coupling coefficient is minus 20 log, right? S31 in here, out here. So, right, power's proportional to the square of this coefficient, right? This so-called, it's basically a transmission coefficient, right? So it's into port 1, out of port 3. So the coupling is also minus 20 log base 10, the magnitude of S31, which is also equal. Then you've got the insertion loss, right, between ports 2 and 1, right? So, right, I'm putting in, remember how this goes, in port 1, out port 2. So the device itself is going to suck some power the design of this is going to suck some power in the energy, in the power going, device itself is going to absorb some power by virtue of its design. So when I input power in port 1, power that comes out of port 2 will be less, right? And so when I insert this device between ports 1 and 2, I'm going to have some insertion loss. And so that's just going to be minus 20 log base 10 of the magnitude of S21. Again, second subscript in, first subscript out, right? And then this is the right coupling, insertion loss, isolation. I is isolation, minus 20 log S41 into 1 out to 4, right? So ideally, whatever I put into 4, nothing comes out of 1. Right? 0, ideal. But the actual device will have some, an actual device will not have 0. It'll be some small number. Okay. And then the directivity, let's see how that works, right? S21 over S41 out of, out of S31 out of magnitude of S31 divided by magnitude of S1. Out of 3 into 1, out of 4 into 1. It's that ratio. So out of 3 into 1, out of 4 into 1. So that's what we call the directivity. Right. So this was designed to couple some amount into port 3. Unfortunately, a little bit of it leaked over into 4. And so you have to take that into account, and that is measured by virtue of what we call the directivity. And so if you look at this, right, directivity is just the isolation minus the coupling by definition. Log of A over B is log of A minus log of B. So log of A is the isolation. Log of B in this case would be the, I'm sorry, plus minus. So when you flip it around, it would be isolation minus coupling. Okay, right. So, right, in example 1011, just as previously, given the coupling, the directivity, the insertion loss, right, and the VSWR. Of course, you'll have a VSWR on these feed lines too. Find the scattering matrix, right? So you can do that, and you can follow example 10.1. That's pretty sure. Okay, let's see. Having to do the notes twice today. This week's starting off a little rough, but let's persevere. Okay. So, right, here's a ring hybrid, right? So, couplers, power dividers, and couplers. So, this is a coupler, right? So, what are we doing here? Right. So here's our scattering matrix representation for the ring hybrid, or the rat race. This is a rat race. It's a rat race coupler, also referred to as a rat race coupler. So power into 1 splits evenly in both directions at ports 2 and 3. So what comes in here comes out of port 2. What comes in here comes out of port 3, and that power is split equally among these 2 ports. Nothing comes out of port 4, or ideally a very small signal comes out of port 4. Why? Because the clockwise distance from the feed line to port 4 is a full wavelength, right? Quarter wavelength plus 3/4 of a wavelength, so full wavelength. Whereas the distance from the feed, from putting power in at port 1 to port 4, is quarter wavelength. The counterclockwise trajectory through the rat race is a quarter wavelength plus a quarter wavelength is a half wavelength. 1 wavelength, half wavelength. So the signals entering this port right here are 180 degrees out of phase and therefore cancel, right? Half wavelength is 180 degrees. 2 pi over lambda times lambda over 2 is pi, which is 180 degrees. And so this signal and that signal are out of phase at port 4. So nothing comes out of here. So equal powers out of port 3 and 2, nothing out of port 4. Okay, so here's our scattering matrix, and that makes sense, right? All right. So that's one manifestation, right? Signals. So in the first case, right, signals fed into ports. Oh yeah, here's another application, right? Signals fed into ports 2 and 3, their sum, right, times minus j divided by the square root of 2 x port 1, right? So we get, if we put signals into 2 and 3, then the signal out of 1 is the sum of these two times a constant, right? So this is just a multiplicative factor, right? And then their differences, right? If I put signals into 2 and into 3, uh, right? The difference exits port 4, comes out of port 4 here and here. The difference, this is the difference signal, right? Because that's 3 lambda over 4, that's lambda over 4. So again, there's a half wavelength between these two, and so that's a difference of the difference between the two signals, and then times minus j divided by the square root of 2. Right, so this thing can sum in different signals. That might be important in demodulation, right? Sometimes in a demodulation scenario, you have to sum and subtract things and add things, right? Another application would be subtracting signals, right? There might be a background signal, right, and a signal plus noise. So you got the noise signal and the signal plus noise. So by subtracting, right, you can subtract out the noise, right? This, so that's an application too, right? Okay, so right, that's one manifestation. Here's another, right? Here's a quadrature hybrid or 3 dB coupler. So note back up here though, right? This impedance is the square root of 2 times Z naught, whereas the impedance of the feed lines is Z naught. So if this were in microstrip, we'd have to modify the width of the rat race compared to the width of the feed lines. Okay. Again, this thing would have some bandwidth characteristics that would have to be characterized as well. Okay, so then the quadrature hybrid, right? 1, 2, 3, 4, 4 ports, right? So here's our scattering matrix representation for that, right? So we go, right, to get out to port 3, right, I've got to go quarter wavelength, right? Uh, 90-degree phase difference between the output ports 2 and 3. Well, that makes sense, right? I put something in at port 1. This goes a quarter wave to get to port 2, whereas to get to port 3, I got to go a quarter wave and a quarter wave, right? So this one is going to be phase lag, if you will, by a quarter wavelength or by 90 degrees, right? So there's a 90-degree phase shift at the outputs between ports 2 and 3. And so the coupling, right, he also points out that the coupling and insertion loss are both equal to 3 dB. Right? So the coupling, right, out of port 3, right, out of port 3 from the input to port 1, right, is 3 dB. And then insertion loss, right, and going from port 1 to port 2, the device itself, right? Here's my port 1, here's my port 2. I insert the device, and so that causes some loss, and the amount of loss is 3 dB. Right? So, so here, right, is right lambda over 4, and here is so the device is symmetrical, right? Rotate it around and get you could take this first column of the scattering matrix and just replace the corresponding elements in the next column. Once this is defined, all these are defined as well. Okay, and then he talks about lastly in this chapter, right? Not in the chapter, but lastly in this section, right? We discuss Lang the Lang coupler, right? The Lang coupler. Right? So these are what we call interdigitated lines, right? So this is a manifestation of microscript. So these things are coupled with vias. These are literally wires started from this line to that line. And so the nice thing about this coupler, right? So input here, right? That's your through port. This is your coupled port. And the amount of coupling would depend on the width of these lines and the separation between these lines, right? You could design that to have a certain amount of coupling. And then this is the isolated, right? So this thing will have, he points out here that it's got good bandwidth, right? So this thing will work over an entire octave. What is an octave? It's a multiplicative of 2 to 1, right? The higher frequency range divided by the lower frequency range of performance, acceptable performance, is in the ratio of 2 to 1. All right, right. He shows you some examples of these, right, uh, using the scattering matrix. So that's pretty straightforward. So, right, here's so for homework on this, homework number 25, work 1033 and 1041. I'll give you a little bit of experience with this. And then, right, our next section is filters, right? So we're going to learn how to design, right, band pass, right, low pass, high pass, band stop, and band pass. So low pass, high pass, band pass, and band stop filters. It's pretty straightforward. Interesting. All right, we're getting there, right? So hopefully this actually recorded rather than not recording. Let's see if I can keep from messing it up. Stop.